I'm Mohammad Ammar. I work for Starline, and I am a resident open source storage technologies. First off, I would like to welcome all of you and thank our partners Magid and Rainer for joining me in this webinar series. Let's start by trying to understand the problem Ceph is attempting to solve and how it solves it. Starting from the bottom up, this is a RAID controller. It's a core component of almost all conventional storage arrays. At the core of this controller, there is a chip with some RAID software on it. You buy a controller and you connect it to a bunch of drives over SATA or SAS. You pop those into a server chassis. On that server, you most probably have some proprietary OS. On top of that OS, there is some proprietary storage management software. You put enough of those in a chassis, and the chassis goes into a rack. You accumulate a number of racks, and you have a data center. But you have been walking towards a trap all the way, because almost every piece of hardware and software you accumulated along the way is proprietary. Now you are in a locked ecosystem with a hefty ownership and maintenance bill. But what if there is a solution that can provide you with all your block, file, object storage needs, and at the same time free you from proprietary lock-ins? Ceph, as a revolutionary open source SDS solution, is trying to unlock your chassis and racks. It's trying to give you full control over your data and enable new technologies and advances that are needed in modern data centers. But what constitutes a SDS? What makes a solution a true SDS? There are 5 core elements in a true SDS. Portability. It should be designed to perform on any standard computer hardware. This eliminates the need to buy proprietary hardware or purchase from a specific brand or manufacturer. Abstraction. It separates storage management from the physical devices, so admins get better and granular controls over storage features. Extensibility. It's support for multiple storage protocols, block, file, and object, which helps consolidate data into a common infrastructure that is accessible to all your clients. Scalability. You can scale storage infrastructure out, up, and down without any service interruption or performance impedance. Application programming interface. It should have an API that can facilitate management and maintenance of storage devices and services. So does Ceph conform to those core elements? Let's check. Ceph is portable. It's as portable as Linux itself. It runs on any x86 or ARM hardware. If you can run Linux on that hardware, you can run Ceph on it. It separates the software from the hardware. You do not have to be a customer of a specific brand or a manufacturer. It is extensible. One cluster can serve iSCSI, SMB, NFS, and modern object storage protocols. In short, all standards and widely adopted protocols are supported. Ceph is also infinitely scalable. Just plug in a new chassis and you can benefit from the new capacity. No downtime is required. And it has a RESTful API that can aid with administration and integration with other systems and monitoring heads. So what are the limitations of conventional storage and why Ceph excels? With conventional storage solutions, only a finite number of disks or nodes or racks can be added to the solution. And almost every newly added node or rack has to be managed independently. This means you need to manage the chassis or a number of chassis through their own management interface, be it a CLI or a GUI. No dynamic expansion or reduction of the storage cluster. Taking ZFS SDS solutions as an example. If you want to upgrade a 12-disk 60 terabyte storage solution to 120 terabyte, you have to replace all 5 terabyte disks with 10 ones. You cannot replace them all at once, and you must go one by one. and you have to wait for the system to finish the bool resilvering process after adding each disk. And downtime is usually unavoidable with hardware failures. Ceph, on the other hand, has no single point of failure. Ceph was designed with redundancy at the core to avoid a process or a component being a single point of failure. It shifts the power to the software layer, makes it open and adaptable. It runs on readily available commodity hardware, no vendor locks. It's self-manageable wherever possible, with self-healing capabilities, but just please don't push it to the limits, and please adhere to the best practices. By the way, this is a topic in one of our future webinars with BetaSAN. Downtime during expansion and regular maintenance, it's not required with Ceph. A fortnight ago, and with the excellent help of BetaSAN's engineers, we have completed a support process for an active petabyte scale cluster without a moment of downtime or client cluster interruption. The cluster was up and running all the time. So what is Ceph? Ceph is basically a group of software services that run atop the Linux operating system. Ceph uses smart and modern AI algorithms to accelerate data I/O and provide data redundancy. By being pure software and open source, and with its smart algorithms, Ceph replaces conventional expensive hardware RAID controllers and proprietary software. It gives you full control over your data, the ability to manage petabytes of storage and scale at any given moment, while at the same time reducing your total cost of ownership. So before we discuss Ceph components, let's have a look at the abilities of the disks we have today. For any given disk, it is still not smart enough for today's technologies and applications. It can send raw data over specific communication channels such as SATA or SAS. It can do basic health checks in a limited self-only manner. It's called SMART for self-monitoring and reporting technology, and it reports back to the operating system. The disk is never aware of where it is, how many other disks exist in the same chassis, where in the rack or data center it resides, and how many other disks exist within the whole cluster. It cannot communicate directly with the client by sending or receiving data from it. Now, we take a quick look at the core services in Ceph. Within Ceph, everything is a software, just remember this. And within any Ceph cluster, you will usually have 5 core services. The OSD, the object storage daemon, where your data is being stored. And this is, in my opinion, the most important one of them. The monitor, and this is the guardian of the cluster. The manager service, which is like the deputy guardian of the cluster. The gateway, which is the channel over which a client can talk to the cluster using a common storage protocol such as SMB or iSCSI. And there is the MDS, the metadata server. Just keep those 5 services in mind. Now, Ceph solves the disk dilemma and limited abilities by creating a smart disk. This is done by pairing a software service that is called the Object Storage Daemon, OSD for short, with the physical disk. Once paired, both are referred to as an OSD. This usually causes some confusion, but just remember, when someone says restarting the OSD or stopping the OSD, they are talking about the software side. If they say replacing an OSD or increasing OSD size, they are talking about the hardware side. And for each OSD in your cluster, there is a dedicated daemon that controls it. So if you have 100 disks, you have 100 OSDs. In a nutshell, the OSD is where your data gets stored. In the most simple form, those are your disk drives, but paired with an additional smart software layer. This layer transforms the relatively dummy disk into a smart data host. They become intelligent storage devices that can take care of stored data. They also get the ability to cross-communicate with each other. with all other OSDs within the cluster over Ethernet, over network. This cross communication is always active, running in the background, and it is what guarantees instant detection of malfunctions within your Ceph cluster. So we created a bunch of networked smarter disks. Now what? You need an independent service to watch over the OSDs, collect and update cluster stats, and govern stability within the cluster. And this is the MON, or the monitor service. Monitors keep order in the cluster by first maintaining a continuously updated map of the cluster. This map contains critical cluster stats, such as how many OSDs, how many monitors, MDSs, and gateways are in the cluster. The monitors also handle client cluster authentication operations. Just also keep in mind that monitors do not store data at all. This is the exclusive function of the OSD. Okay, I have a cluster, but how can my client machine access the data on that cluster? There are two ways your client can access the cluster, either directly via librados. Librados is a piece of software that you can install on your client, and it immediately gives it the ability to talk to Ceph, or through a common protocol gateway. This is basically another Linux machine with Rados installed on it that can connect to the cluster and serve storage over iSCSI or NFS or SMB to the client. In this case, the gateway needs to be able to install librados to expose the cluster to the client. So in a nutshell, librados is the common language your client needs to be able to speak to communicate directly with the Ceph cluster. Otherwise, you have to run a gateway. So again, if you want to use Ceph as iSCSI backend story for your VMware servers, an iSCSI gateway will help you bridge the communication between your VMware server and the cluster. The gateway here communicates with the cluster, passes the exported LUNs to the VMware server, and you're done. And you can run multiple types of gateways on Ceph, iSCSI, NFS, SMB, and S3 or Swift. Ceph also provides access to POSIX compliant Ceph FS. So our cluster is here, and we have networked OSDs and monitors. What about metadata? Metadata is everything related to your data except the data itself. And for a picture, the metadata would be when it was created, when it was last modified, and who has permission to access it. And a Ceph metadata server stores the file metadata on behalf of Ceph FS. And you only need a metadata server if you plan on to use Ceph file system. To sum things up, you have 5 critical services running on each Ceph cluster: the OSD, which stores your data; the monitor, responsible for monitoring and stability and authentication; the manager provides additional monitoring and interfaces with external monitoring and management systems; the metadata server stores metadata on behalf of the Ceph file system; the gateway exports data to the external clients using a standard protocol. And here is an overview of a Ceph cluster with 3 gateways and clients. You remember the first slide with the RAID controller? It had a chip with a RAID algorithm on it. So where the smartness of Ceph comes from? This is the RAID controller, just for a quick refresh. And the smartness of Ceph comes from Crush. Ceph has the equivalent of that algorithm that was on the RAID controller. Actually, it has a much more advanced and sophisticated algorithm at its core that is not only able to replicate data, but it can also monitor, rebalance, and automatically recover data on your behalf in the event of a disk or chassis or even a whole rack or site failure. That smart algorithm is called CRUSH. It's short for Controlled Replication Under Scalable Hashing. CRUSH controls where and how your data is stored in a Ceph cluster, provides better data management mechanisms compared to older RAID approaches, and enables massive scalability by cleanly distributing the work across clients and OSD daemons in the cluster. Yes, Ceph clients can offload work, and they can communicate directly with the OSDs. And you know how is that possible? It is possible because also Ceph clients understand and can run CRUSH. How does it work? How does a client that wants to store data on a Ceph cluster act? It's simple. On your client, you install librados or the Ceph command libraries. Once installed, if the client wants to store an object on the cluster, and because it has a bit of CRUSH smartness, it runs the object ID through CRUSH. This produces the destination OSD and buckets in which the data needs to be stored. The client then can directly communicate with the OSDs to store and retrieve the data. And this does not only avoid bottlenecks, it also prevents a single point of failure and allows for unlimited scalability, since all parties are aware of each other and are capable of communicating with each other without having to go through the monitors. This is how a client cluster I/O goes during daily operations. You can see the client first goes to the monitor. Once authenticated, it can go directly to the cluster to access and retrieve data. Finally, I would like to say that I always recommend to think of Ceph as a modern AI-powered RAID over network. If this is your first time listening to a Ceph intro and you are still struggling, that's totally normal. Just think of Ceph as a RAID over network, but instead of the RAID controller hiding away its proprietary algorithm in a protected chip, Ceph charges every single member of the cluster by allowing it to use its smart algorithm. CRUSH is that algorithm, and then the client and the components can act as smart and independent members. This smartness extends all the way to your client, so it can fully interact with the cluster without a proxy. Let's quickly reflect on the core components of Ceph clusters that we mentioned in our previous episode. If you didn't join, then I would recommend to check the video recording for it. In Ceph, everything is a software layer, and there are 5 core software daemons. There are the monitors, the OSDs, the managers, the metadata servers, and the gateways. Monitors are responsible for monitoring and stability and client authentication. You need at least 3 of those. OSDs are what's responsible for data storage. You need as many of those as you could to guarantee good throughput and data resilience. The manager is there to provide additional monitoring and interfacing with external monitoring and management systems. It runs parallel to the monitor. The metadata server stores metadata on behalf of the Ceph file system, which means you only need it if you plan on using Ceph file system. The gateway exports the data to external clients using standard protocol, so it acts as a pathway for data reads and writes. If your client cannot directly use librados, which is part of Ceph software, then you will probably need a gateway for iSCSI, NFS, and SMB. Basically, you need a gateway for all clients that cannot directly deploy and use librados to connect to the cluster. We also said that those components use the same CRUSH algorithm, which is the smart brain of Ceph. CRUSH is short for Controlled Replication under Scalable Hashing. It controls where and how your data is stored in a Ceph cluster. It's also used to define your failure domains. Those are the cluster components that you can afford to lose without the cluster going offline or losing or interrupting service. It provides better data management mechanisms compared to older RAID approaches and enables massive scalability by cleanly and evenly distributing the data and the work across all clients and OSDs in the cluster. Ceph clients can contribute work to accelerate the overall I/O of the cluster. This is possible because Ceph clients can use Crush to quickly calculate which placement groups or OSDs to send or fetch the data from. Crush creates an initial map for your cluster containing all your OSDs, chassis, racks, aisles, and even geolocations. And this map is used to pseudo-randomly store and retrieve data in the OSDs, and all the members have copies of this map. Once it gets updated, all the members will receive a fresh updated copy of the map. So Ceph is a redundant clustered storage system where all members of the cluster are networked, actively interacting, and always aware of each other's status and function. They all benefit from Crush, and Crush's smartness extends all the way to the client. Ceph clients can use Crush for data placement or destination calculations. I would like also to highlight that any client that uses Librados to connect to a Ceph cluster actually knows that it's connecting to a clustered setup. So it knows that it's connecting to a distributed storage cluster, and all other clients that connect over gateways like over iSCSI or SMB, they are unaware of the fact that they are connected to a clustered system. What they can see is only what's presented to them by the gateway. If it was an iSCSI LAN, they can only see the iSCSI LAN. If it's an NFS or an SMB share, they can only see the SMB share. The Librados clients, they know that they are connected to a clustered system. And with its particular architecture, Ceph functions as a smarter RAID over network system where data replication and recovery is collectively guaranteed by all of this cluster's members. Let's take a look at the basic mechanisms of how data is stored in a Ceph cluster. We have two basic mechanisms that Ceph uses to store data. First, replication, which is pretty simple. You take an object, you duplicate it an X times. The default value for Ceph here is 3, so the default replication number is 3. Take this object, replicate it 3 times. Each object will yield 2 more copies, so you have 3 copies. Those 3 copies go to live on in 3 different placement groups on 3 different OSDs. The other mechanism, which we can see here, is erasure coding. Erasure coding, on the other hand, is a calculation process, and it requires some processing of the data before it gets stored. So we take one object, and here we're using erasure coding setup of 3 plus 2, 3 original data chunks plus 2 encoding or resilience chunks. So we take an object, we split it into a number of k chunks. We add some coding chunks that can be calculated using the erasure coding algorithm, and then we know which destination placement groups this can be sent to, and we send it to the cluster. So replication, one file, replicate this file X times, it gets sent to 3 different placement groups on 3 different OSDs. And this graphic is oversimplifying, and the purpose is just to emphasize that we will end up with 3 copies of the file. But the trick is that we're not actually duplicating the file, we're duplicating or replicating the object. Sorry. So here's the smart bit. Your client, when it's sending the data to the cluster, it only needs to send the object or the file once, and it sends it to the primary OSD here, and this primary OSD will take this file, send it to the secondary OSD, because we said that the replication, the default replication within Ceph is 3, so we have to end with 3 copies of the file. The file sent to the primary OSD will take it and replicate it to the secondary and make sure that the tertiary OSD gets a copy, and now the client here will receive an acknowledgement that the data has been saved. This is important to note because if you have like 100 terabyte of raw storage and you decide to use replication within your cluster, you will only get about 33 terabytes of maximum usable storage. But there are 2 tricks here. One, there is a near-full ratio of 85% for Ceph. Once you fill your cluster to 85%, you will get a warning that you're approaching a full status. Now, once you hit 90%, and this is predefined also in Ceph's configuration, once you hit 90%, your cluster becomes read-only, and you will not be able to add write data to it until you add more OSDs. This is very dangerous in case you're running iSCSI applications, like you're using the cluster for your virtual machines, because all your virtual machines are going to crash. So erasure coding, take the file, split it into a number of K chunks, then using the erasure coding algorithm, calculate and add the coding chunks, the black ones here, and then send those to the OSDs or the placement groups on the OSDs. So in the event of an OSD failure, if we lose this yellow OSD here, the Ceph cluster will basically ask all remaining 4 OSDs to send the data. It will calculate the missing chunk based on the available 4 bits, and then this missing chunk will get written to a different OSD. But you should here note the overhead, because you have to split the data first, and then you have to calculate some encoding chunks, and then you can write. And there is also the overhead when reconstructing the data, because you need to read from the remaining active OSDs, basically recalculate the missing chunk, and then save to the healthy OSD. I also would like to note that when using erasure coding, it's recommended to set the M value, which is the number of coding chunks or recovery chunks here, to a value of 2 or more to prevent data loss. So with erasure coding setup like 3+1, that's not really safe, because in the event of one OSD node failure, this can eventually lead to data loss, because like you're left with a very critical number of data bits, and one more OSD goes down and your data is gone. So 2 or more when using erasure coding is the best approach for safety. Don't go below 2 erasure coding chunks. So replication versus erasure coding. Replication is more space-wise expensive because it uses more disk. Erasure coding, on the other hand, requires more processing, which means it's CPU and RAM. It's more CPU and RAM expensive than replication. Because that, if you plan on using erasure coding, you should account for this computational overhead when selecting your hardware. So I mentioned placement groups multiple times so far, and I think it's important to know what they are and why Ceph uses them. So let me quickly show you this slide. In this slide, I need to focus on three things. First, in Ceph, you need to create pools for your data. Those are logical containers spanning multiple disks. Pools are mapped to a group of disks. So our pool, which is the gray rectangular here, is mapped to this set of disks. Second, data is always stored as an object. So the file gets split into a number of objects, and those objects get sent to the cluster to be stored in placement groups. Okay. Third is that placement groups are mapped to OSDs. So pool mapped to disks, placement groups mapped to pool is mapped to disks. Objects are mapped to placement groups, which are stored on those disks or on those OSDs. Now I think it's useful to try and break down the placement groups concept. But before we do so, let's try to agree on one thing. In addition to high performance and data security, all modern and scalable storage systems or solutions out there are trying to achieve some goals. So all scalable storage systems are trying to do this. They want to distribute the data evenly between the member disks or nodes. At the same time, the system wants to achieve the least possible amount of data migration in the event of capacity change or hardware failure. So if you add more nodes to the cluster, or if you lose a node, or if you lose a disk or OSD, the system wants to achieve the least amount of data migration in such event. And those 2 points are the core functionality of, or the core logic behind the use of placement groups. To better understand placement groups and how they can improve performance, we should first take a look at a regular RAID setup. So this is a RAID group. It's a mirrored RAID group. In this system, we have, it's basically a three-way mirror. So we have 3 copies of each entire disk. In this system, each disk is mirrored to 2 more disks, and the data is mapped directly to the disk. And for this setup to actually function, we need disks of matching capacity. An entire disk like this disk here must be mapped, completely cloned, not just mapped, completely cloned to 2 more disks. So even though that you end up with the capacity of a single disk here, or 4 disks, you have to use 12 disks, okay? And for recovery, an empty spare disk is always required. That spare disk must also be of the same capacity. So we need X number of disks plus some spare disks of the same capacity, or basically the same model for data recovery. Now, let's simulate a disk failure in this basic setup. This disk here fails. When this disk fails, the RAID controller or the RAID software will detect the failure, and then it will check for a spare disk. This spare disk is found, and it gets activated. The RAID controller will now look for a healthy member disk within the RAID. It finds this guy, and then the RAID software or the RAID controller will start cloning the entire disk from here on the spare disk. When you look at such setup, you realize that there are some sort of limitations here, because with such approach, first, an empty disk is always required for recovery. It's just a piece of hardware that you spent money for, and it's sitting there doing nothing until you run into some issue. 2, a completely healthy disk containing a full mirror of your entire data set is also required. And third, the entire disk gets cloned onto the spare disk. This means that the recovery duration is going to be limited to the throughput of either disks. So if your disk here can read at a much slower at a slow rate, then your recovery duration is going to be extended, because basically you want to wait for every single block of this disk to be cloned to the spare disk. Disks are much bigger now than they used to be 5 or 10 years ago, and the larger the disk capacity, the longer it will take you to recover, and the longer your RAID system or RAID setup stays in a recovery mode, the wider your vulnerability window is, and you need to get over this ASAP, but your disk is already running and at its limit, and you cannot do any better. And before the initial disk failure, you already had to spend money on the spare disk, which was not optimal. Finally, if you are so unlucky to lose 1 or 2 more disks during the recovery, you're in a dire situation, because a good chunk of your data is gone. Now let's simulate a disk failure in a Ceph cluster, where we use placement groups as buckets for data. So quick backwards, we said that file gets split into objects. Objects gets assigned to placement groups, which reside on OSDs. Okay, so we split an object. We split a file to multiple objects, and we send the object according to the crush algorithm to be replicated 3 times across the cluster. So initially we had this green object, we had 3 copies of it. We had 1 copy here, 1 copy here, and 1 copy here. But this disk failed, and this disk was actually the host for 2 different placement groups, not just the green one, but the green and the blue one. So we are looking at a 3x replication, middle disk fails, and because all cluster members are aware of each other, after 5 minutes or 300 seconds of this initial disk's demise, and it not being able to report its status back to its friends within the cluster, it's being declared as down. Now the secondary and tertiary OSDs for this placement groups, this green placement group is going to be contacted. Okay, so we have this guy here, and we have this guy here. They're going to be contacted by Ceph, and the cluster goes into a health warning status, which is unhealthy for Ceph. The cluster pseudo-randomly looks for an OSD with enough empty space to contain only the lowest to contain only the lowest amount of data, or to contain only this placement group. And we find this guy, and this guy contains enough space to host a copy a third copy of the placement group, and it gets regenerated from 1 OSD and copied here. Same thing happens to the blue one, where we can find the healthy copy. Sorry, this arrow is inverted again. This arrow should be going from here to here. We find the healthy copy of this blue placement group on this OSD, and we send it here, and now we're ending up with 1, 2, 3 of the blue, 1, 2, 3 of the green. So compared to a classic RAID group, this mechanism does not require a disk containing a full mirror of the dead disk. We only need a disk containing healthy copies of the lost placement groups, the green and the blue. Okay, and when this means you just lost a portion of the data, not the entire data set when you lost 1 OSD. This also causes the least possible amount of data migration, because you only needed to copy this amount of data onto this disk, not the entire disk. So network saturation is going to be minimal in this condition. No spare disk was required. Of course, we only need enough space on any OSD available within the cluster. And finally, multiple or simultaneous disk failures can rarely cause data loss, because the placement group would all 3 copies of the placement group should never reside on the same OSD. You would never have all 3 green bits residing on this same disk. You will have them distributed randomly within your cluster based on your crush failure domains configuration. So also Crush allows you to specify your failure domains, and those are basically the components of your cluster that can go down without causing service interruption or data loss. With such approach, if you had hundreds of OSDs hosting thousands of placement groups, in the event of a single disk failure, the aggregated throughput and the minimal contribution required from each OSD can greatly decrease recovery duration, getting you back to normal or to stable and healthy condition much faster. Smart and simple. It's also worthy to note here that even during recovery, the cluster will continue to perform. If your cluster is well configured, if your failure domains are well configured, your clients will continue to be able to perform I/O to the cluster. With this very basic explanation of the process, we can define BGs as data buckets that are mapped to OSDs, whose sole function is to host objects and generate the least amount of data migration in the event of a single OSD failure, or in the event of an OSD failure. I would also like to note that all storage systems, all modern scalable storage systems achieve those goals in a similar way. In Swift, placement groups are called partitions. So if you are familiar with Swift, placement groups is basically what partitions are in Swift. So again, referring to the concept of Ceph being a smarter, more efficient RAID over network, it's important before we get into hardware selection for your Ceph clusters to say a few words about Ceph's networking and its considerations. Because everything within Ceph is done over Ethernet, is done over network, it's critically important to use the best networking infra your budget can afford. Always use 2 separate networks for your cluster. One network that goes to the client. This network connects to the cluster members, primarily the OSDs and the monitors and the gateway, and it leads directly to the client. It's called the front network, and there is a separate back-end network that is used exclusively by Ceph's cluster members, excluding the client. Use 2 separate networks, one for your clients, one for the Ceph nodes to communicate with each other. This will not only improve performance, but it will also protect your data in case one or more client gets compromised. If this client gets compromised, this will affect only the data set or the amount of data that that this client was allowed to have access to. If you use a combined network, then the attacker can basically penetrate the entire cluster, and this can be very dangerous for your data. Also, never go below 10 gigabit. Actually, with the price gap between 10, 25, and 40 gigabit hardware decreasing every day, we currently recommend going for 25 or better whenever possible. If you plan on running a SSD-based cluster, and with the considerably higher throughput of a single SSD or NVMe compared to a spinning disk, a 25 gigabit infrastructure should be your bottom line for SSD or NVMe deployments. 10 gigabit translates to about 1 gigabyte per second. You can easily saturate this network with a properly configured 4 nodes hybrid cluster. 25 gigabit translates to about 3 gigabytes per second, and you can easily saturate this network with a properly configured 4 nodes SSD or NVMe cluster. Imagine what you can do with 10 or more nodes. Now, one might think, okay, I will use 10 gigabit for my front end here, so the clients can get the maximum throughput, the best throughput my budget can afford. And I will use 1 gigabit for the cluster's backend network. That will save me some money. Yeah, I'm smart. Wrong strategy. And here's why. Because we just said the backend is what's used for OSD data replication. So when you send, if we go back to this slide, we said that the client sends the data to the primary OSD, and then the primary OSD is going to contact 2 more OSDs for data replication, and this is going to happen on the back-end network. So when we go back here and we look at this, if you use 1 gigabit here, this is what is going to happen. The back end is what's used for OSD data replication. The back end is what's used for OSD data regeneration and redistribution, the recovery process that we just discussed with placement groups. So because your client will not receive an acknowledgement from the cluster until all 3 copies of the object have been stored, your client will have to wait longer for each acknowledgement because the data replication between the primary, secondary, and tertiary OSDs is happening here on the suffocating 1 gigabit network. Okay? So how did the 75 euros less per interface help you? It did not. So bottom line is, buy the fastest networking gear for the specific application or throughput you need for your cluster and clients, and it's recommended to add some more bandwidth padding for future expansion. Also, whenever possible, use the same bandwidth for front and back end. If you have to save, then don't go below 10 gigabit on the back end. So, piecing some things together, selecting your cluster hardware can be confusing, especially with some contradicting information that one can find online. But yeah, let's say this: what do we know so far? Everything is a software. We need to know how much CPU, RAM, and disk and network resources those daemons, those software daemons, require to happily operate and exist within the cluster. We also know that Ceph has different components, with the most critical being your OSD, and this is where you want to focus your attention and your budget, because we don't want to starve. We do not want the OSD to starve for resources, especially CPU and RAM. Mons can coexist with OSDs. This means you can run a monitor service on the same OSD chassis where you store your data. It's not optimal and it's not the best practice, but it's possible, and Betasan supports this. You can choose this when you're doing the Betasan installation, and your monitor will happily coexist with within the OSD. Clients can either use a gateway or directly use Librados to connect to the cluster. So you need to consider this application scenario. If your client can only connect using iSCSI, then you have to run a gateway. And this gateway needs some resources because it needs to connect to the cluster, fetch the data, and serve it to the client, and vice versa. We know that we can replicate the data or use erasure coding to encode the data. We know that replication is more space consuming, but relatively more performant, especially for small scale clusters. Erasure coding is CPU and RAM expensive. It uses more CPU and requires more RAM. It also has a relatively slower write speed, especially for small scale clusters. We know that we can use Crush to define our failure domains. Yeah, so before we start to wonder how much hardware can like 300,000 euros buy me, or saying I need a full SSD 20 nodes cluster, there is some homework. There's some very important homework that you have to do. First, you need to define your use case. just resist going nuts with your monies. I'm always happy to sell you a Lamborghini, but I will always advise you to go for the Audi S6 Avant if it's the best solution for you. Narrow down your actual throughput and IOPS requirements. Be exact about your failure tolerances, like how many OSDs, hard disks, to be more specific, I can lose, or how many OSD nodes I can lose. Do I have to run one aisle or two different aisles, or two different data rooms, or two different geolocations? You have to be more exact about your failure tolerances. And check your existing networking and hardware infrastructure. Anything that conforms to the following tips and tricks about selecting hardware, you can keep it, and anything below 10 gigabit you should discard and should not be counted. So with those points being highlighted, let's take a look at the hardware recommendations from some Ceph resources that are available out there online. Ceph's official blog, Red Hat, and SUSE's recommendation. Side by side, we can see that Ceph recommends to use 64-bit CPU, that you should use one CPU core per OSD, 5 gigabytes of RAM per OSD, 10 gigabit networking, co-location of services is possible. This is basically like running your monitors and gateways and OSDs on the same chassis. They also recommend using separate front and back end networks. Red Hat says use 64-bit CPU, one CPU core per OSD, 5 gigabyte RAM per daemon, 16 gigabytes of RAM for the operating system, 10 gigabit networking. Co-location is also possible, separate front and back end networks. SUSE is here, although being the trickiest, but they say 64-bit CPU, one logical core. Please note the difference. One CPU core is different from saying one logical core per OSD. They basically mean that with CPUs that support hyperthreading, a hyperthreaded core can count as a core allocated to each OSD. 4 gigabytes plus of RAM per daemon, 10 gigabit networking infrastructure, co-location is possible, monitors or OSDs, gateways on the same node, separate front and back end networks.